Hello, pre-calc. So we are starting chapter 2 where we're going to look at patterns graphically, numerically, different ways, verbally. This might be a long video, so you might want to break it up into like first page and then watch the second page later. That is totally up to you. So we're going to start off with linear functions and constant functions because you should all know what those are. So we know that a linear function looks something like that, usually not with a little squiggle in it like I just did, but you know what I'm doing. And here would be a constant function. So your parent graph, the parent function we know is y equals x. And x, if it's a constant, then makes it a constant function. You guys have several variations. You have your slope-intercept form, which everyone always seems to prefer. Not my favorite, actually. Y equals mx plus b, where we know that m is your slope, which means you do the rise, difference in the y's, over the difference in the x's. That's your run. And the b value is where you begin when you're graphing it. That represents your y-intercept. My favorite, because it's actually more applicable as you're getting to know more equations, is called point slope, because you don't have to solve for that y-intercept. It just takes an actual point and the slope, and you have your equation. And it really comes from just cross-multiplying your slope formula, if you think about that. Also, something to notice, in a linear equation, and we're going to talk about this as we get into one that has it, there is no concavity, because concavity is when you have a curve in your graph. And is it curving upwards or curving downwards? Well, line is straight, so it has no concavity. So then we want to go through and find the equation of the line. First thing we always have to do is find the slope. So we take our 2 points. I always kind of like to put them, you guys are big kids, I'm not going to go through the specifics of this. So here's the difference in my 2 y values over the difference in your x values. You have to do it in the same order, otherwise you will mess up your slope. So this is going to give me 15 on top over a -5, which simplifies to a lovely -3. And here is why I prefer point slope. I can choose either point, really doesn't matter. I'm going to choose the second one just because I like it. And point slope would give me y minus the y value equals the slope, and then times x minus the x value, and you're done. However, if you had to put it in y equals mx plus b, because sometimes that's helpful when you're comparing two lines and you want to compare, I don't know, their slopes and y-intercepts and all that, what I would do is I just distribute that first one. So I'm just going to isolate y. So up above I have -3x plus 30. So I'm still going to have a -3x, but that plus 30 I add 6. So this would be the other form. All right, so there's your linear equation. Next, we're going to move on to your quadratic equations. So if you remember, I'll kind of do a little example. If a is positive, we know that positive people smile, so that would look like that. And if a is negative, negative people frown. So that one would look like that. Now this one does have concavity. So this top one, when a is positive, you are, what I abbreviate is CU, that's concave up, because it's like a goblet. The concavity is facing upwards. If it's the frown, I abbreviate that one as, that is concave down. We'll be talking about concavity from time to time as we move through the year, because that actually plays a big role when you get into calculus. All right, quadratic functions, parent function, most basic quadratic, y equals x squared. And then you have several forms for your quadratic. You have standard form, and that one looks like y equals ax squared plus bx plus c. When it comes to you in that form and you have to find, I should keep the same color, if I had to find the vertex, and this is what we just did in our station activities, you would do opposite of b over 2a at the beginning of your quadratic formula, and then plug that in to find the y value. That would give you your vertex. Then you guys have vertex form, which is nice because that one shows you the vertex right away. That's y equals a x minus h squared plus k, where your vertex is hk. And then lastly, you have what's called the intercept form. And this one is when you can graph based on when it comes to you in factored form. So I'll say x minus, oh my goodness, I'll just put a c here, and x minus c2. Your vertex is going to, it's going to fall halfway between those. C1 and C2 are your intercepts. So these are your x-intercepts, and the vertex is going to lie on the average of those. Okay, I'm writing really tiny. I'm very impressed with myself. Some of you guys like to write tiny. Okay, that's how you would find your vertex. And so yes, and you have your concave up and your concave down. Now the fun begins. This is a review problem, but we expect you guys know how to do these. Okay, find the equation of the quadratic function that goes through these 3 points, because you have to solve for a, b, and c. Those are 3 variables, so we need 3 equations. So we're solving a 3 by 3. Later on, we'll show you some shortcuts for doing this that you don't have to use by hand. So to do this, we are going to be using standard form. So I'm going to start off with this point. And so that's going to be 76 equals, and I'm going to be plugging in 1 for x. So it's going to be a times 1 plus b times 1 plus c. That was lovely. Now we're going to plug in this equation. So we have 89 equals, now we're plugging in 2 for x. So this will be 4a plus 2b plus c. And then lastly, which color shall she use? Let's use green. So then we have 94 equals, so this is going to be 3 squared times a plus 3b plus c. Now you might think, oh my god, a 3 by 3, but this is actually because c is always just plus c by itself. It's kind of friendly. What I like to do, and again you can do any way you want, I like to take this middle equation and I multiply everything here by a -1. So as long as you do it everywhere, it's fine. Then I'm going to add these two because my c is going to go away. So when I add those two, I'm going to get 76 minus 89 is a -13. That's going to equal a -3a minus b. All right, now I'm going to add the last 2 equations. 94 minus 89 is going to give me 5, and this will give me 5a plus b. Look at how nice that is. Okay, so then there's our 2 by 2 that we immediately got, because it got rid of c, so I can add these together. That gives me -8 equals 2a. So I now know that a equals a -4. And everything else is just going to be back substituting. So if a is a -4, I'm going to plug it in here. So I'm going to have 5, I'll do it down here because I'm going to just read my solutions up there. So I have 5 equals 5 times -4 plus b. So that means b is going to equal 25. And to get that last variable, which is c, I'm going to go to my original equation, and I have 76 equals, a is a -4, b was a +25 plus c, And when we solve that out, we get c equals 55. Used to be the speed limit. All right, so we have to put it all together though. So y equals a negative 4x squared plus 25x plus 55. See, that wasn't that bad. So using standard form, if you make that middle equation all negative, it actually comes out really quickly. All right, now we're going to get on to our power functions, and I'm going to do the best I can to be organized in this because there's many different variables going on here. Parent function y equals a times x to the b. So notice x is your base and your power is the exponent. And I'm including a in our parent graph just because you'll usually have to deal with that. Okay, so we have some examples down below, but what I want to try and do, I should have made sort of a chart for this. Let me do it two different ways. Okay, if a is positive, so we have a positive a, and b is also positive, then what you have, and again, b could be a fraction or it could be an integer greater than 1, but what this is going to give you is a direct variation type of graph. So in other words, as x is increasing, y is increasing. So something like, I don't know, can I do that? Yeah, I'm going to go ahead and do it. And I'm doing it in the first quadrant because you'll tend to find, again, in this book, he tends to keep it in the first quadrant for these for the power functions. Now, what happens if, let's say, b is negative? So if b is negative, when you have an exponent that's negative, remember that goes in the denominator, so then you have your inverse variation, which might look something like this. Okay. If we wanted to talk concavity of these functions we just wrote, this one right here is concave up because it's like your hand is cupped upwards. This one would be concave down. This one is also concave up, just so we can identify our concavity. Now, what if b or a is negative? You know what? I'm going to make life easy for myself. If a is negative, then you are just reflected over the x-axis. I'm going to take a little shortcut here. Ta-da. All right, is there anything else I want to talk about? Okay, so when we look down below, we notice that 1/4 x squared, that is concave up, that is a power function, where your b is going to be greater than 0. Here b is still greater than 0, but notice it's a fraction. So if b is between 0 and 1, in this case, it is concave down. Like a square root function would be concave down. It's still a power function. And then here b is actually negative, but we are concave up. So that's your inverse variation. And look, I gave you a little graph just for the fun of it. Okay, so we want to be able to come up with the equation of a power function. And I probably do this maybe a little different than you might have done in A2A. So that's good. You might learn a different method. There is more than one way to do it. I think your old A2A book used substitution. I'm not a big fan of substitution, but you know, you can choose whichever method you like. So here was our parent function again. Oh my gosh, look at that. She almost wrote it wrong. Dun, da, da. X is your base and your power is b. There we go. All right, what I like to do is I like to take the value that has the higher y value first. You'll see y in a second, and I write that one out. I fill everything in first. So 192 equals a, which we don't know. The base is the x value, so that's going to be 16 raised to the b. Raised to the b. All right, underneath it I write the other one. So the y value is 24 equals a times my base is 4, the x value raised to the b. All right. The reason why I do that is because everything here, notice, is multiplication. So I'm going to divide the two equations against each other. And the reason why I like the bigger one on top is so I don't have a fraction when I do that. But it doesn't matter. You could. It really doesn't matter. So what I'm next going to get is 192 divided by 24 is a lovely 8. Notice that now my a values are going to cancel, so I'm free to only solve for the b. Now, 16 to the b over 4 to the b, remember, I'll write it off here to the side, is the same thing as 16 over 4 raised to the b. So what I have here is 4 to the b. Now, solving for an unknown exponent, there's two ways we can do this. You can think about it and reason it out, or you can use logs. I love logs, and we're going to review logs later in this chapter, so I will do this two ways. No, I'm not going to do it two ways. We'll show you why it works after we do it. So it's a good review of your logs, which is coming up. So if I take the log of both sides, sorry guys, I love logs. By taking the log of both sides, remember, well, I'll do it step by step. Okay, so I have 4 to the b. It allows you to remember this guy can travel down in front. So I have log 8 equals b times log 4, and I'm now free to divide both sides so that I can isolate b. And if you go to your handy dandy calculator, it will tell you that b equals 3/2. So that's really cool. Let's test that this really works. So they're saying 8 equals 4 raised to the 3/2. So remember what that means. That denominator means you take a root. The numerator means you raise it to a power. So the square root of 4, remember, is 2. 2 cubed is 8. It works. Awesome. So we found b. We still have to find a. So I can plug it into either equation, or it really doesn't matter. Now I'm going to use my smaller numbers. So I have that 24 equals a times 4 to the 3/2, which we now know is 8. So 24 equals a times 8. So we know that a is going to be 3, and we put it all together. Y equals 3 times x to the 3/2. All right, that was fun. I forgot I got to do logs. That's what happens when you're a math teacher. You get excited about silly little things. All right, exponential functions. Your parent graph shall look very similar to the power function, except now your base is b and your exponent is x. And it only makes sense if we keep b positive and b cannot equal 1. Because otherwise that's silly. 1 to the whatever is always going to be 1, except unless it's infinity. But that is for later. Okay. So we have y equals a times b to the x. And again, we're going to look at, you have several cases that could happen here. So if a is positive, so we're going to keep a positive for a second, and we're going to keep b greater than 1. Remember, now we're going to keep b positive, but that means it could be greater than 1 or it could be a fraction. So if it is greater than 1, like, 2, 3, whatever, what you have is exponential growth. And usually you pass through a. So we have our y-intercept is a, because b to the 0 is 1. 1 times a is a. So we call this exponential growth. And if b is between 0 and 1, obviously not equal to either, then you have exponential decay. However, you're still passing through a y-intercept of a. This is going to be your exponential decay. And just like before, I'm going to take a little shortcut here. If a is negative, then basically you reflect over the x-axis. I'm not going to draw them out because that's a vertical reflection. All right, so if we look down here, we have 1.5, so b is greater than 1, so this one is exponential growth. And notice all of these, well, no, that's not true. So when a is positive up here, I should probably write this here, you are going to be concave up, regardless if it's exponential growth or decay. When it reflects, what happens is it becomes concave down. So on this next one, here is our exponential decay, because our b value is between 0 and 1. And here you have the -2, so that one is concave down, whereas both of these were concave up. Concavity tells you something about acceleration, believe it or not. So that'll be pretty fun to investigate later on. Now, we do want to come up with the equation, and we need 2 points because we have 2 variables, a and b, to solve for. So we have our parent function, a times b to the x, and I know it looks like these really crazy numbers, but it actually, they are chosen because it's going to come out really nice. I do exactly the same process because notice how power and exponential, they kind of look the same, it's just b and x switch positions. I solve them exactly the same way. So I start off with the bigger y value on top. Doesn't really matter, it's just my preference since I'm the one who's solving it. And then a times b cubed. Underneath it, I chose the other variable, so this will be 6.5 equals, oh boy, did I make this one easy for you? Okay, so notice again, everything's multiplication. So I'm going to divide the two against each other, and believe it or not, 10.985 divided by 6.5 is 1.69, and the a's will cancel, and then b cubed over b1, when you're dividing, you subtract exponents, so this will be b squared. And then how do you solve it? Now with these ones, you're not going to do a plus or minus because we want b to always be positive. So you don't have to worry about that aspect of it. You just go ahead and take the square root of both sides. Remember, the square root of 169 is 13. So in this case, b is going to be 1.3, which is kind of nice. Now we still need to solve for a. So we come up here and we choose either of the 2 points, really doesn't matter. 6.5 has a few less numbers to it, and we plug it in. So this is going to be a times my b value, which is 1.3 raised to the 1. Ooh, that's going to be a tough one. That was sarcasm, sorry. 1.3. And so, believe it or not, that also turns out 65 divided by 13 is a very friendly 5. And I should probably square that. All right, and we have to put it all together. So y equals, drum roll please, 5 times 1.3 to the x. Now, I don't know, however you want to write it. Some people write 5 parentheses 1.3, then close parentheses, whatever. Realize this is not, this is my cautionary tale. These two, the 5 and the 1.3, you never multiply those together. Okay, it's, here is your function that is getting multiplied by 5. So you can't do 5 times 1.3 and then raise it to the exponent. It's 1.3 raised to that exponent and multiplied by 5. Okay, I'm done. Hope this was good, and have fun doing the expiration.